So we've seen the difference between samples and populations. Now we're going to continue with that discussion. First thing we want to note is about the quality of our estimates. So what we saw was that we could take a sample and that would give us a guess of the population, standard deviation and mean. What we need to know is that the quality of our guess, so I just call it the quality of our guess, depends on the sample size. So here's the setup. So this is some data that I just simulated, and I ran through some examples to see how much variation I was getting in my sample estimate of here the sample standard deviation. So how good was my sample standard deviation estimate? So I know what the mean is, I know what truth is, and you can just see as my sample increased, so I've got 100 observations in the population, but as my sample increased, all of my guesses get very close to the true mean. So that's one of the things that we just need to be aware of. When we think about this, when we have a small sample, the quality of our guesses might not be so great. Like we could actually be, it could turn out that our guess is really quite close to the true population mean or standard deviation, but it could be that we're relatively far away. But once we have a reasonable sample, and you can just see here I've shrunk it to 25, so samples of 25, really getting quite tight. You know, I think, at least for me, that looks like a pretty tightly clustered group of guesses. So that's what we need to be aware of, that the quality of our guesses improves with sample size. So that's why we tend to talk about the value of higher or larger samples. Now we want to move on to some key propositions. So these are the most fundamental propositions that we're going to work with. So the first one is, if you take a random sample from a normal population, the distribution of the sample means. So that means that if you took a sample and you calculated the mean from that sample, so not the shape of the distribution of the sample, but the distribution shape for the distribution of mean. So if you took repeated samples and calculated the mean for all those samples, you'd have a distribution, and we call that the distribution of sample means. So the idea is that if you're taking samples from a normal distribution, and for each sample you calculate the mean, those means also follow our normal distribution. And I think that probably is intuitive. You can just say, okay, yeah, everything we're doing is from a normal distribution. Okay, everything makes sense. So distribution of sample means would also be normal. Proposition 2 is a little bit more tricky. It says, whatever the underlying population distribution, if I take a sample from that distribution and I calculate the mean, and then I take another sample from that distribution and calculate the mean, and I plot the distribution of the means. So I'm not looking at the actual samples I take, I'm looking at the distribution of the sample means. Whatever that population that I'm taking samples from, the distribution of sample means is always normal or approximately normal. And the final proposition is that the distribution of sample means is much smaller than the overall population mean. So these are three essential propositions. Proposition 2 is derived from the central limit theorem, so we're not going to derive that, but what I'm going to do is I'm going to click through now to some simulations and demonstrate these properties to you. So what I've got up here is a normal distribution with mean 12 and standard deviation 2. And what I'm going to do down here is take various samples of different sizes and see what happens when we calculate the mean and then plot the mean. So you can see here this first sample is a sample of 16 and we've got the mean 11.92. So it's quite a good guess of our population mean, which we know up there is 12. So let's, before I do that, let me drop this down to samples of 4. So if I start taking samples of 4, you can see that my estimate of the mean jumps around quite a bit. So when I've got small samples, my guesses are not so great. But let me bring this back up to 16 and let's see, again, you can see that when we've got samples of 16, our guesses about the mean are pretty good. Now what I'm going to do now is I'm just going to click accumulate, and so each sample I take, I'm going to plot the mean of the sample. Okay, so let's click sample, and you can see that each time takes a sample, so there it is, and it's plotted it at 11.6, another sample 11.3, next one 11.8, and so on. So what I want you to take notice of is the distribution that's forming down here. You can see it's starting to have that bell-shaped curve, much like the population distribution that we're sampling from. So let me just run this for a while now here, and it'll zoom along. And so I think it's pretty clear that if I run this for long enough, ultimately it's going to generate some sort of bell-shaped curve. The other important thing to notice about this is the shape, okay? So the shape of the distribution is much tighter than up here for the population. Now I'm just going to up this again and say, let me take samples of size 64. So we clean it away again, and I'm going to keep accumulating. So I'm going to calculate the mean and plot it. Okay, so here we have 11.8, and let's just run this, and I won't do too much other than let it accumulate. And what you can see now, if you recall, the shape of the distribution when we were taking samples of size 16 was much more spread than the distribution when we're taking samples of size 64. So we've seen a couple of things here. We've seen that when you take samples from a normal population, calculate the mean, the distribution of the sample mean is also normally distributed, and we see that it's much more tightly distributed than the original population mean. Okay, and there are actually some theoretical relationships here, so we can have a bit of a look at that. So you can see here, if we take samples of 1, our sample mean is just going to be the same. But as we increase the sample size we take, the distribution of the sample means gets tighter and tighter and tighter. And this falls at the square root of n. That's the rate that this thing falls at. So you can see we had a standard deviation of 2 up here. When we have a sample size of 64, we divide through by the square root of 64, we get a quarter. All right, so the next thing, so that one's not too tricky. We do have this idea that the sample mean distribution becomes much tighter, but the shape sort of intuitively makes sense to us. The next one is a little bit more unusual. So here we have our population here. We've got something that's very much clearly not normal. I hope we all agree that this shape up here, it doesn't look anything like our traditional bell shape. Now, rather than take samples of 2, or we might do, let's take samples of 2. If I took samples of 2, I'm going to see this sample mean distribution accumulate. And what you're going to see is the distribution of sample means also has nothing like a normal distribution. In fact, the distribution of sample means when I'm taking samples of 2 from a population that has this shape is pretty much going to give me back the original population shape. So you can see that this thing that's accumulating down here looks nothing like a normal distribution. And what am I plotting down here? I'm plotting the distribution of the sample mean. So let me do something here, and let me start taking samples of size 32. So now I'm going to take samples from this very much non-normal distribution, highly skewed distribution. This is the sort of extreme that you can push this theorem that we're working with to. And now I'm going to take samples, and down here I'm going to plot the distribution of the sample means. So let's do that. So I start running this. You can see all the samples accumulating here. And if we run this for long enough, what we're going to see happen is that the distribution of sample means is going to start to resemble our classic normal distribution shape. So again, it's much tighter than our population, but the shape is nothing at all like the population shape. What we've got instead is something that is approximating a normal distribution. So we've seen this empirically. We've just seen you can see this is the population up here. We keep taking samples from this population, calculating the mean and plotting it. And if I just click this through here, you can see that this is the sample. So when we have samples of size 1, we get back exactly the population distribution. But as my sample starts to increase, that tail starts to disappear, and you can see already by sort of sample sizes of around 20, it's starting to look pretty much like a normal distribution. And by the time we've got up here to about 30, I mean, just to the eye, this distribution that we're looking at here is very, very difficult to pick that from different from a normal distribution. So what we've established is that when you take samples from a non-normal distribution and you consider the distribution of the mean of the samples, that distribution is also normally distributed. And that is flowing from the central limit theorem, and that's the proposition I wanted to demonstrate. Thank you.